Good morning. This is Tim Stewart. I am president at Visual Decisions, and we're here today to talk about Industry 4.0 impacts within process industries. At Visual Decisions, we've been in the business of utilizing information from the shop floor to improve continuous improvement since about 2002. We help our customers combine the smart factory with the lean factory to drive improvements to cost, throughput, and quality. Our customers have seen dramatic improvements such as 30% increases in OEE, 50% scrap reductions, and much more. We have a unique approach to work with our customers to adapt processes to take advantage of the new capabilities that Industry 4.0 can provide and establish a true data-driven manufacturing culture. So I'm going to start off by talking a little bit about Industry 4.0, but I just want to make a procedural note. If you have questions, please enter them into the Q&A, and I will get to them either during the event or at the end of the presentation. So Industry 4.0 has a very, very broad set of technologies that it encompasses. We're going to really focus on three of them today. The first of them is the Industrial Internet of Things, or I-IoT. And for those that don't know, this usually is a platform that consists of several primary components, such as data collection, data routing and persistence, event processing, communication, development environments, machine learning, and AI systems, which we'll cover in a second, and usually has a very, very highly extensible API. Usually they ship with fairly little functionality out of the box, but the idea is that they provide a complete toolkit to build just about any application within the sphere of I-IoT, which is a fuzzy term that encompasses just about anything if you ask the right person. On the subject of AI and machine learning, these are technologies that allow computers to really think either as humans do or provide cognitive capabilities parallel to what humans can do. And so they can do pattern recognition, they can do matching, they can do all kinds of different tasks to supplement the people within your operations. Augmented reality is a newer capability compared to I-IoT and machine learning, where you are looking at the real world, but as an overlay, you can see information, work instructions, how the process is performing, any number of different overlays over the current real world view that you have. And this can either be with a phone, as shown in the picture here, or with glasses such as the Microsoft HoloLens or RealWear, or a number of different pieces of hardware that do that. So one of the questions that I get when I talk to people in the process industry is around MES and the ISA 95 stack and so forth, and how that overlaps with some of these things that we're talking about, in particular with IoT. And so if we look at it, MES or MOM systems are widely deployed throughout many process industries. And conforming to ISA 95 has been an obstacle to Industry 4.0 adoption, as there are strong biases towards the existing standards and the solutions that are built to conform to those. And some of the early hype around IoT, several years ago, really kind of failed to look at the high connectivity already present in the process industries. But if we look at the primary strengths of each system, there's room for them to work together. MES is primarily a system of record that has decades of development and refinement behind it. It's extremely well established with its functionality, with its data models, and existing integrations to different systems as well. Usually composed of a broad suite of solutions that are underneath that header, and it is built to be a common system across different manufacturing sites within your organizations. When you look at IIoT, it's primarily a system of improvement. It's made to work in the way that supports your processes for quality and for process engineering and so forth. It's generally built on more modern architectures. So the advantage of MES is it's been around for decades. The disadvantage is it's been around for decades. So I-IoT systems generally have more flexibility in their platforms and built for more connectivity and so forth. It's also built as a hub for shop floor. So it doesn't look to own the data. What it looks to do is connect and pass information along. And it can be the center of a lot of different best-in-class solutions. So if you have existing systems on the shop floor already, what it can do is really patch those together so that they work together much more cleanly. And it easily coexists with those other systems. So some specific use cases where you might look at IoT to supplement MES. Plant communication, if you digitize paper-based plant data into dashboards to transform existing analog data into real-time information, that way you can use that knowledge. This becomes a powerful asset for artificial intelligence and machine learning implementations, dashboards on screens, laptops, mobile devices, provide those process controls within your organization and so forth. Predictive maintenance, it was real-time data to use to predict when equipment will fail. And instead of performing maintenance on an arbitrary schedule or on a preventive maintenance set schedule, you can do it only when it's necessary, guided by when the systems let you know that it's required. Interfaces between different systems, as I said, a lot of companies in the process industries already have, enterprise resource planning, supply chain management, customer resource management, quality management systems, laboratory information management systems, warehouse, MES, SCADA systems, human resources, and more. And most of these are, somewhat isolated, where the data and information exchange is somewhat rudimentary. But using IoT and technologies such as, or standards such as MQTT or OPC UA, REST APIs, and so forth, you can do a lot to bridge the information from these different systems and really have them work together much more cleanly. You can enhance existing data collection utilizing these tools, and we'll talk some more about that later. But you have the ability to deploy very advanced sensors outside of the equipment itself and pull that information into IoT to supplement the data that you're collecting through the PLC itself. Real-time process optimization and predictive control. So deploying AI or ML can deepen the understanding of how a plant operates, and building upon your employees' past experience, predictive operational control and real-time process optimization will further improve quality, reduce safety issues, and optimize energy and raw material consumption. And then energy management itself is something that the process industry relies on: utilities, electricity, steam, gas, water, and energy management is necessary to limit those costs. And energy management focuses on the collection of energy data to achieve certifications like ISO 50001, which are typically used for tax benefits and so forth. So as I said, you can also build custom applications on an IoT platform that really supplement what you have with other systems. And certainly some recent webinars I've talked about building custom visual controls. One area that is very common to do that within process environments is total productive maintenance is very common within process industries. And your TPM boards can actually be automated using these tools so that you can spend the time using the information from those boards to make your process more reliable, as opposed to having people spending their time just updating those boards on a continuous basis. You can integrate information from this into process FMEAs that you might have. and utilize the information to make those live so that they don't get done once and stuck in a drawer. You can create a digital management operating system, taking those TPM metrics and so forth, and actually having those live and be something that is integrated into everybody's standard work, so that you can create that true operating system for your business. And then value stream mapping is another example capability. Another large opportunity is building an OEE system the right way. So most MESs will have some OEE capability within them, but usually it is somewhat limited. And one of the things that we will see is how to really build a tremendously robust OEE system. And I'll talk about that for the full webinar next week. But really the possibilities here are endless. It's, whatever, edge cases you want to put in place, you can basically put them all in place with IoT. And one more note here is that, if you're rolling out an MES system across multiple plants, usually, where you get bogged down and where that starts taking a lot of time is when you have to do a lot of customization from plant to plant. And one of the things that you can get the benefit from if you're putting in an IoT along with a MES system or an MOM system is that you can have that core system really focus on what it does really well as acting as a system of record. And then a lot of these other use cases and so forth that we'll discuss today, you can put into the IoT system and have that be something where you can manage that and the variability in those edge cases from plant to plant while you roll a consistent MES or MOM application across your different facilities. All right, so process industry and key challenges for Industry 4.0. And there's a lot of challenges in every industry, and process industries are no exception to that. But some particular key challenges that we'll look at today are product safety, along with recall and traceability and quality assurance, and then productivity and managing complex supply chains, as well as a lot of you have continuous flow, but then you also have mixed mode production process facilities. Applications within process industries. So product safety, recall and traceability. One area where technology can make a huge difference is enhancing product safety. Product shelf life is a real issue for many process manufacturers who have to be careful to control the flow of products and not overproduce. Electronic traceability can play a significant role in solving this issue, allowing producers to track items from delivery to the supermarket shelf or other end consumption points. And smart sensors are being included in packaging to measure changes in microbial activity, temperature, pH, oxygen, CO2 levels, et cetera, which will provide a more accurate method for detecting spoilage compared to less accurate best before dates and things like that. It can also look at product recalls, food and beverage, as well as other process industries. Recalls may become necessary due to consumer complaints or inspections, and pressures growing on manufacturers to institute product recalls as quickly as possible. The traceability of contamination, however, is a complicated matter, as several factors such as some of those microbial impurities, labeling and packaging errors, contamination by metals, plastic, glass, or other potentially dangerous substances such as machine oil or biohazards have to be taken into consideration. And therefore processes have to be put in place to identify and eliminate sources of error. So, one way that this can be done is through, advanced sensors and I-IoT. They contribute greatly to this effort. There are many varieties of, intelligent identification systems, which enable better traceability. For instance, in certain, kind of farm to plate industries, instances. You have RFID labeling tracks, or tracks crops right from harvesting in order to be able to trace the origins of the cargo. And you can institute things like blockchain tracing across different entities to be able to maintain that certification as you go throughout the entire supply chain. And there are also other systems that allow systematic and efficient data tracking from all the way from raw material to the end product. So where does that information flow? As you take in all of this sensor information, you'll feed it into the IoT platform as well as your systems of record, which then combines the information coming from the machine itself, other systems, and other sources to be able to put together the complete context of what's happening on the shop floor. Information sources don't just reside at one individual station. Context from other areas is important. This gives you the ability to create that complete context of what's happening on the shop floor to give information back to the operators with work instructions and visual controls to enable your frontline workforce to make the best possible decisions in the context of more global information. So as we're asking our operators to take on more and more of the burden of doing decisions, creating more autonomy within the workforce, and pushing decision making as close to that front line as possible, we have to give information to those people not only about their individual process, but how that process is functioning within that global perspective. And so being able to create that integrated work cell is critical to enabling that process. Environmental monitoring is also extremely critical. From that perspective, you have to be able to track conditions with environmental sensors. This can help make certain that the environment is cold enough or dry enough or whatever is necessary within your operations. You can look for cold or warm spots, even in the same room, fine-tune the ventilation and so forth. It also enables documentation and certification within your facilities so that materials have been, you can certify that materials have been stored properly the entire time. And it can also provide any alerting, if things are starting to get out of acceptable tolerances, trending the wrong directions, et cetera. You can alert whoever needs to know, and they can take appropriate action. Along those same lines, for the entire cold chain certification, you can have sensors and communication basically at every step of the process. I'm showing a food chain here, but the most relevant example these days is probably the vaccine cold chain certification, and being able to ensure that each vial of the vaccine has been stored at the appropriate temperature throughout the entire process from manufacturing and beyond. Quality is closely related subject here, but if we think about quality, all quality is the result of some source of variation. So if we think about a typical Ishikawa or fishbone diagram, you've got machine, man, method, materials, etc. And we'll take a look at a few here. So from a machine perspective, variability exists in nearly every manufacturing process. And certainly as you put these advanced sensors in place, you connect up to the PLCs, you pull information together from those, from different testing systems and so forth. You have the ability to perform that analysis across different processes, look at causal analysis by looking at some of that tag data and combining that with the process information and so forth. You can create customized workflows and analysis tailored to the environment. You can take a lot of the design of experiments and so forth that you would do and actually put those within a workflow built right into your IoT tool so that you can perform these studies and help your people with that process. So if you're trying to roll out green belts and yellow belts and so forth within your organization, you can really build that right into your system and have that capability to support them so that they don't have to remember all of their schooling and Six Sigma practices to be able to do that. So I'll give some examples throughout this presentation, and I'm going to be utilizing examples from one of my IoT partners in PTC with ThingWorks, as well as their Vuforia solutions for AR and so forth. And in this example, what we're doing is we are utilizing real-time production performance monitoring and getting a real-time view of that performance of the machine, as well as some of that broader context as well. Get out of the box KPI reporting for OEE, mean time between failure, mean time to repair. If you're more interested in those topics, I did a whole series on maintenance and how you can maximize your mean time between failure, minimize your mean time to repair, as well as maximizing your first time fix rate the other day. Preventing causes of variation from a manpower perspective. Often our largest sources of variation are the people in the process. And this kind of varies a little bit. Continuous flow, the people may not be as big of a source of variation, but certainly in batch manufacturing and so forth, that possibility is there. So, why are most human errors happening? Is it, lack of proper training? Is it lack of discipline? Or do they just not have the information available that they need in order to make the correct decisions? And so some of the things that we talked about earlier, for instance, having that connected work cell and so forth, can give them more information, can provide the standard work, and really help them do the job, in the best possible way. You can also utilize some of these same tools to do much more error proofing. It says pick and place, apologize about that, but much more error proofing in terms of how they set up the machines, what the recipe management is looking like, within that operation and so forth, and identify variance between different operators for operation time, setup time, downtime, etc. Methods are certainly another source of variation that you have within your operations, and really this is all about being able to easily maintain the work instructions and then get those out to the people, and then identifying where people deviate from that standard work or standard procedures, and correct it. And so these tools can be very helpful in identifying those causes and putting steps in place to remediate it when necessary. AR also helps address those challenges because it's one thing to look back and forth between the operation that I'm doing and then looking at a computer screen that tells me what my recipe is supposed to be, come back to the machine and make adjustments there and so forth, go back to the book and look up what are the machine settings supposed to be, and then come back to the machine and do that again. Where I'm very much dividing my attention between different visual cues and so forth. With AR, I can overlay everything right on the asset itself, and I can have my work instructions actually right there so that I can see them as I'm interacting with the process itself. It also gives me the opportunity for remote assistance. So if I'm looking at doing things like minimizing downtime and so forth, if I'm pushing from a TPM perspective, autonomous maintenance, out to the operators and so forth, being able to get them real-time assistance when necessary for either newer people or people they're at a new process and so forth. This way you can have the people do that, and for all the routine things they can go through it, but if they run into something that they don't expect, or they need to troubleshoot something, or anything outside of normal, they can very quickly use their phone, use a tablet, etc., and connect with one of the experts in the operation without having to wait for that person to get out to the machine in order to help. And so the augmented remote assistance capabilities have a tremendous impact on being able to really drive that autonomous maintenance capability, as well as supporting the irregular maintenance crew when they go out to the machines. And then, of course, coming back to the digital and augmented work instructions that we talked about earlier. Productivity and throughput. So in this area, you have just tremendous capabilities that, the IoT and the, artificial intelligence, machine learning are going to provide. So not only do you have the basic, asset monitoring utilization capabilities within, your existing systems, you can augment those, pulling in additional information, pulling in, outside information from additional sensors and so forth. So noise or vibration sensors, being able to, get that information into it. Things that you might not have hooked up to a historian in the past, such as a pump or, a valve, and so forth. You can connect up to the IoT, and you can actually now take information in from those and, look at your pressure and your cavitation showing up as vibration and so forth, noise, etc. And now you can utilize that information to help control and optimize the process as well. Predictive maintenance allows you to take the information from all of those tags and so forth and actually do your predictions on when you believe that machine is going to have problems. And I'll give a detailed example of this on the next screen, but this can be, around maintenance, it could be around quality. Those are the most common use cases. But, if you have tooling and so forth that, is can be worn, those are things that can be predicted as well. So a customer example here, going through and looking at a machine part replacement and using machine learning to know when to perform that maintenance to prevent quality issues. For some of these wear out parts and, tooling in some, industries, as well as just, machine parts in others, knowing when to, change that item is something that, is typically done either on a preventive maintenance basis where you say, every 30 days or every, 10,000 units, we're going to, replace this and put in a new one, something like that. You have the ability to now look at the metrics coming from the process itself and utilize that to make those decisions. And so you have machine PLC information, you have additional sensor information such as vibration, noise, power consumption, time series data, et cetera, feeding up into, a basic model that you have built in an IoT platform such as ThingWorx. This information can then, feed into that model where you're doing the predictive capabilities and also just representing, uptime, downtime, and, basic OEE information as well. And then you can take the outputs of that modeling and understand, when you should be changing, different items, whether, again, it's the tooling or different spares, et cetera, and then present that information on a computer, on mobile, through AR, et cetera, and, have a very flexible capability of, making those things happen. You can also transform your improvement process. This is a typical 6-step process, but if you look at each step within here, the reliance on data is huge. So identifying the problems within the facility, knowing where your biggest problems are and being able to address those first, analyzing the current process, creating solutions with an expanded solution space, utilizing these capabilities, simulating those changes before you put them in place, and invest in capital and so forth, measuring and analyzing the results to ensure that you're supposed to get what you that you're getting what you expected, and then standardizing the solution both within that process so that it doesn't revert back to previous behaviors when the team moves on, as well as standardizing the solution across different lines and so forth. Root cause analysis is usually the one that everybody just nods their head, where anything that you can do to enhance the data collection and the analysis capabilities is going to be looked at as something that is going to provide value. And whatever root cause analysis framework you're using on an individual project, whether it's something as basic as who, what, when, where, why, how, or the 5 whys, or an Ishikawa diagram, or just doing graphical evaluation, or doing a full process FMEA, or utilizing Six Sigma tools such as ANOVA, DOE, et cetera. All of those, you want data, you want to be able to say exactly what's going on in the process and have that all be data-based analysis. Complex supply chains, certainly there are key trends in warehousing and distribution that are relevant here. Smart glasses, vision picking, help employees kind of effortlessly pick items and transport them to different zones in the warehouse. End-to-end inventory tracking, and from the product's arrival to the warehouse to its delivery to a shopper's doorstep. Manager will be provided with status updates, a location within the tracking system for the warehouse, and notifications in case of any complications. Data analytics, and being able to look at what is the value of all the different information that you're getting from all the different sources. Just one example here is fork trucks, and if you're tracking your fork trucks using IoT, RFID sensors, or anything along those lines, you can now analyze how efficient is your fork truck usage, what is your loaded versus unloaded time from a route optimization perspective, having analytics in place around that, being able to look at where you leave something like a pallet jack, when it's not being used. You can optimize the location of storage for those things based on usage patterns throughout days and so forth. So tremendous capabilities for collecting additional information and utilizing that within the warehouse as well. Vision picking, I touched on a minute ago, but smart glasses help employees effortlessly pick items and transport them to that different zone. Connected wearables have intuitive interfaces. Learning to use them takes less time than memorizing the location of different types of goods and having to reach it manually within the warehouse. The vision picking systems also reduce the amount of paper documentation and track product lots automatically, increasing the productivity of the warehouse. Next, we have automated material handling systems. So that instead of having your workers having to determine flow and so forth, all of those things can be done automatically. And a lot of these things can be done at much higher speed, with the kind of modern controls. And then keeping it up and running, you can sense the vibration, the noise, the voltage again, and being able to use your machine learning to identify where you're having upcoming failures, and being able to put maintenance in place to keep those up and running as much as possible. And vision systems, being able to utilize those to automatically inspect for damaged goods and other issues. So just a kind of a quick note on mixed mode production and having common systems upstream and downstream. Within a lot of different process industries, you have continuous flow in a lot of chemical, industries and so forth, and you're putting those in bulk, out into, trucks to, go to its next usage point and so forth. But many industries within, the process world, pharmaceuticals, food and beverage, a lot of different chemical companies and so forth are, bottling, packaging, their goods. And so they have the upstream side where they have batch manufacturing typically, and then you have the downstream side with packaging, bottling, packaging, et cetera, and shipping. And so being able to utilize common systems across those different sides of the house, and being able to present common interfaces for people within the plant can be very valuable. especially if you have one continuous improvement team for the plant and they're trying to look at both sides of the operation. Being able to go into one system to be able to do that is tremendously valuable and gives a lot of leverage to the organization as a whole for being able to get the best possible use out of these different systems. And so with that, thank you for your time this morning. I don't see any questions in the Q&A right now. So if you do come up with questions afterwards, please reach out to me at tim@visualdecisions.com or my phone number below. And I'll probably reach out to you or have one of my associates reach out to you in the coming days to follow up and see what we might be able to do to help you within your environment. So thank you very much, and I look forward to talk to you next week about OEE systems. Thank you. Bye.